Okay, we have here an interesting problem with the golden ratio. What we want to find is just the golden ratio to the 8th power. And we'll use a couple of definitions we have over here. We're just going to use the phi symbol as some shorthand, so I'm not writing this thing out over and over again. And then an interesting property, look, the reciprocal of this is really similar, it just changes the sign. And also we have the formula here for the golden ratio squared. We can just express it as golden ratio plus 1. You can kind of mess around with the values to see how some of this works. Like you can, on your own, do that out, add 1 here. When you're adding 1 here, you can do it as 2 plus 2, and you kind of see what happens, because you'll get the same thing if you square it out. So some of this I won't do out all those details, because it's going to be very easy for you to square some of these out. If you want to multiply it out or square some of this out, you can do it on your own. Now to get started with it, I know multiple ways to do it. I mean, the obvious way is you could just start multiplying it out or use binomial theorem. I'm going to skip all that. It's kind of tedious. I don't know if it's that much longer, but you start thinking though, what if it was the 12th power, the 20th power? Multiplying it out, it's not that great, but it would work, so you can do it that way too. What I want to try to do is use some shortcuts on it. Like first, if we've got phi to the 8th, I can break it up and write it as phi squared to the 4th, which is going to allow me to use this formula right here, right? I can plug in, we can kind of reduce the power just through this formula. So now I can write this as just phi plus 1 to the 4th, or doing the same thing we did before, breaking up the power again, write it as phi plus 1 squared to get our 4th power. Then when you multiply that out, you get phi squared plus 2 phi plus 1 all squared. But then I can just apply this formula again, plug in phi plus 1. Now we have, adding it to this, right? We're going to have 3 phi now. 1 plus 1, 2, all squared. Square it out. We're kind of just repeating the same thing. This gets much worse if we're dealing with like the 15th power, because we have to square it out over and over and over again. I do have another method for that coming up, but right now we're just doing it over and over again. So when we square that out, we get this thing. Then we use the same trick again on this, plugging in phi plus 1, so we end up with 9 phi, distributing in 9 to this, plus 9, plus 12, plus 4. Combine that together, we're going to have 23 times the ratio plus 13. So now, I think to get it all the way back, let's now use our definition and distribute in 23 to it. So let's see what's going to happen. Did I make a mistake somewhere? I feel like I made a mistake. Oh, you know what? 9 plus 12 is 21. My bad. So we got 21 phi right here. And so we'll distribute in the 21. Doing it, we're going to have 21 square root of 5 plus 21, just using the definition, over 2. And then 13, let's get a common denominator, 26 over 2. Putting that together for the solution of this, we get 21 square root of 5 plus 47 over 2, and that's going to be our answer. Okay, let me clean up the board and we'll move on to method number 2 on this. Okay, so for another way to look at phi to the 8th, this part may seem a little strange at first, but we can look at this thing, because this thing with the golden ratio tends to be pretty nice and has a lot of nice properties. And what I'm going to do with this is let's add something else that's pretty nice. Same kind of thing, but with the negative. When you add these two together, what's going to happen is this is going to cancel here. You're going to get 2 copies. We don't want that. We just want 1 copy. So for this whole thing, I can divide it by 2, and this is going to be phi to the 8th. Now, this is definitely overcomplicating things for sure, but the reason it goes quick with this is because we have such a nice pattern with this and this that instead of doing really any work, we can just know the pattern. So let me show that and we'll see how that works. Okay, I just wanted to show the first few examples to get a feel for how this works. Again, you can easily get to these by just squaring it out. Like even, okay, the first one there, all we did is just add these 2 values together. It's easy to see that half and minus a half is going to cancel to give us this. So you can kind of just get a few values to get a feel for it just by squaring things, like square this and you can get away to this value and you can establish a few of them. But the key thing is to know this pattern, that if we kind of go, okay, so we change the sign, look, we have, like, notice that the sign is alternating, but like we have the square root of 5 stays with us, and that's going to keep going, just alternating with the plus and minus version. Same pattern as this. And then same thing here, we just have a number increasing. But now on the square root of 5, notice I kept the 1. The reason is because the pattern with this is just going to be the Fibonacci sequence. There is a formula that's not, I don't think it's quite applicable here, but it's related, that shows us that this is related to the Fibonacci sequence. 1 plus 1 is 2. The next one, 1 plus 2 is 3. Fibonacci sequence. Here, I think technically this is not considered Fibonacci because it doesn't quite match up, but it's still the same kind of thing because we take 1 and 3 and we get 4. And then for the next term, it's going to be 3 plus 4 and a 7. I guess this method you could say isn't that great if it was like the 25th power, because then you're still doing the Fibonacci sequence to 25. But when the exponent's 8, it's not going to be too bad. And we kind of see how it works over here, that we just have the Fibonacci sequence on our coefficient here. And so we can just kind of count up to our answer. So using this over here on the right, we'll just kind of use the sequence to get to our 8th value. What we're going to have for the coefficient on the square root of 5 is going to be, let's see, 1, 1, 2, 3, 5, 8, 13, 21. That's going to be our 8th value right there. So we'll stop with that. Then with this integer term here, same kind of thing. We can go 1, 3, 4, 7, 11, 18, 29, and then 29 plus 18 is 47. So all we need to do is put it in this form. So we're going to have 21 square root of 5 plus 47 over 2, and that's it. So anyway, there you go, golden ratio to the 8th power. Thanks everyone for watching. Have a good day.